Today we are going to discuss the basic operating principles of three-phase motors, list factors that produce a rotating magnetic field, list different types of three-phase motors, discuss the operating principles of squirrel cage motors, connect dual voltage motors for proper operation on the desired voltage, discuss the operation of consequent pole motors, discuss the operation of wound rotor motors, discuss the operation of synchronous motors. Determine the direction of rotation of a three-phase motor using a phase rotation meter. Three-phase motors are used throughout the United States and Canada as the prime mover for industry. These motors convert three-phase alternating current into mechanical energy to operate all types of machinery. Three-phase motors are smaller, lighter, and have higher efficiencies per horsepower than single-phase motors. They are extremely rugged and require very little maintenance. Many of these motors are operated 24 hours a day, 7 days a week for many years without any problem. These are the three basic types of three-phase motors: squirrel cage induction motor, the wound rotor induction motor, and the synchronous motor. All three-phase motors operate on the same principle, and they all use the same basic design for the stator windings. The difference between them is the type of rotor used. Two of the three motors are induction motors and operate on the principle of electromagnetic induction in a manner similar to that of transformers. In fact, AC induction motors were patented as rotating transformers by Nikola Tesla. The stator winding of a motor is often referred to as the motor primary, and the rotor is referred to as the motor secondary. The principle of operation for all three-phase motors is the rotating magnetic field. Three factors cause the magnetic field to rotate. First is the fact that the voltages in the three-phase system are 120 degrees out of phase with each other. Second, the fact that the three voltages change polarity at regular intervals. And third, the arrangement of the stator windings around the inside of the motor. Synchronous speed is determined by two factors: the number of stator poles per phase, and the frequency of the applied voltage. In many types of machinery, the direction of rotation of the motor is critical. The direction of rotation of any three-phase motor can be changed by reversing two of its stator leads. This causes the direction of the rotating magnetic field to reverse. When a motor is connected to a machine that will not be damaged when its direction of rotation is reversed, power can be momentarily applied to the motor to observe its direction of rotation. If the rotation is incorrect, any two line leads can be interchanged to reverse the motor's rotation. When a motor is to be connected to a machine that can be damaged by incorrect rotation, however, the direction of rotation must be determined before the motor is connected to its load. The direction of rotation can be determined in two basic ways. One way is to make an electrical connection to the motor before it is mechanically connected to the load. The direction of rotation can then be tested by momentarily applying power to the motor before it is coupled to the load. There are occasions when it is not practical or is very inconvenient to apply power to the motor before it is connected to the load. In such a case, a phase rotation tester can be used. Many types of the three-phase motors used in the industry are designed to be operated onto voltages, such as 240 volts and 480 volts. Motors of this type, called dual voltage motors, contain two sets of windings per phase. Most dual voltage motors bring out 9 T leads at the terminal box. Three-phase motors can be constructed to operate in either Y or delta. If a motor is to be connected to high voltage, the phase windings will be connected in series. This is called the delta connection. When a motor is to be connected for low voltage operation, the phase windings must be connected in parallel, or Y connection. Voltage and current relationships for dual voltage motors. When a motor is connected to the higher voltage, the current flow will be half as much as when it is connected for low voltage operation. The reason is that when the windings are connected in series for high voltage operation, the impedance will be 4 times greater than when the windings are connected for low voltage operation. Squirrel cage induction motors receive its name from the type of rotor used in the motor. A squirrel cage rotor is made by connecting bars to two end rings. If the metal laminations were removed from the rotor, the result would look very similar to a squirrel cage. A squirrel cage is a cylindrical device constructed of heavy wire. A shaft placed through the center of the cage permits the cage to spin around the shaft. A squirrel cage is placed inside the cage of small pets such as squirrels and hamsters too. Permit them to exercise by running inside of the squirrel cage. The squirrel cage motor is an induction motor. That means that the current flow in the rotor is produced by induced voltage from the rotating magnetic field of the stator. When power is first connected to the stator, the rotor is not turning. The magnetic field of the stator cuts the rotor bars at a rate of 1800 RPM. This cutting action induces a voltage into the rotor bars. This induced voltage will be the same frequency as the voltage applied to the stator. The amount of induced voltage is determined by 3 factors: strength of the magnetic field of the stator's number of turns of wire cut by the magnetic field. In the case of a squirrel cage rotor, this will be the number of bars in the rotor, and the speed of the cutting action. Since the rotor is stationary at this time, maximum voltage is induced into the rotor. The induced voltage causes current to flow through the rotor bars. As current flows through the rotor, a magnetic field is produced around each bar. The magnetic field of the rotor is attracted to the magnetic field of the stator, and the rotor begins to turn in the same direction as the rotating magnetic field. As the speed of the rotor increases, the rotating magnetic field cuts the rotor bars at a slower rate. The amount of torque produced by an AC induction motor is determined by 3 factors: strength of the magnetic field of the stator, strength of the magnetic field of the rotor, and the phase angle difference between rotor the stator field. Sum of the factors that determines the amount of torque produced by an induction motor is the strength of the magnetic field of the rotor. An induction motor can never reach synchronous speed. If the rotor were to turn at the same speed as the rotating magnetic field, there would be no induced voltage in the rotor, and consequently no rotor current. Without rotor current, there could be no magnetic field developed by the rotor and, therefore, no torque or turning force. A motor operating at no load will accelerate until the torque developed is proportional to the windage and bearing friction loss. Wound rotor induction motor is very popular in industry because of its starting torque and low starting current. The stator winding of the wound rotor is the same as the squirrel cage motor. The difference between the two motors lies in the construction of the rotor. Synchronous motors have several characteristics that separate it from the other types of three-phase motors. Some of these characteristics: synchronous motor is not an induction motor. It does not depend on induced current in the rotor to produce a torque that will operate at a constant speed from full load to no load. Synchronous motor must have DC excitation to operate. It will operate at the speed of the rotating magnetic field. Synchronous speed, it has the ability to correct its own power factor and the power factor of other devices connected to the same line. Word Selson is a contraction derived from self-synchronous. Selson motors are used to provide position, control, and angular feedback information in industrial applications. Although Selson motors are actually operated on single-phase alternating current, they do not contain three-phase windings. Selson motors actually operate as transformers. The rotor windings is the primary and the stator winding is the secondary. Thank you, and please like, share, and subscribe.